For millennia, humanity has gazed upon the crimson beacon in the night sky, Mars. Once a distant star, it now represents more than just celestial wonder. It symbolizes our next great leap, a potential lifeline for the future of our civilization. The race to conquer Mars isn't merely about flags and footprints. It's a profound necessity for the long-term survival and evolution of the human species, a multi-generational endeavor driven by both ambition and an urgent sense of planetary preservation. Our home, Earth, is a vibrant oasis, yet it faces unprecedented challenges. Climate change, resource depletion, geopolitical instability, and the looming threat of extinction-level events remind us of our singular vulnerability. Placing all our eggs in one planetary basket is a risk we can no longer afford, pushing the exploration of Mars from an adventure into an imperative for survival itself, a crucial step in safeguarding our collective destiny. Mars offers not just a sanctuary, but a vast, untouched frontier. Its unique environment holds keys to understanding planetary evolution, the origins of life, and fundamental cosmic processes. Moving beyond Earth provides unparalleled scientific opportunities, pushing the boundaries of human knowledge and inspiring generations to pursue scientific and engineering advancements with unparalleled vigor and ingenuity. The very act of venturing to Mars forces humanity to innovate at an accelerated pace. Every challenge, from efficient propulsion to sustainable life support, demands breakthroughs that inevitably yield terrestrial benefits. These spin-off technologies improve life on Earth, fostering new industries, creating jobs, and driving a global wave of technological progress and economic growth that benefits all of humanity. Historically, humanity thrives on exploration. From charting oceans to ascending mountains, our spirit is defined by pushing boundaries. Mars represents the ultimate frontier, a challenge so immense it can unify nations and rekindle our innate drive to explore the unknown. It offers a common goal, transcending earthly divisions and inspiring a renewed sense of collective purpose and monumental achievement. The psychological impact of embarking on an interstellar migration is profound. It forces us to reconsider our place in the cosmos, to think on multi-generational timescales, and to forge a new identity as a multiplanetary species. This shift in perspective can foster a deeper appreciation for Earth, while expanding our vision for what humanity can truly become across the galaxy. One of the most compelling arguments for Mars colonization is planetary protection. A catastrophic event on Earth, be it an asteroid impact, a supervolcano eruption, or an uncontrollable global pandemic, could decimate or even extinguish our species. Establishing a self-sufficient colony on Mars acts as an insurance policy, a crucial backup copy of humanity, ensuring our continued existence. Resource scarcity on Earth poses a fundamental threat to future generations. From rare Earth elements to clean water and fertile land, our planet's finite resources are being consumed at an unsustainable rate. Mars, while seemingly desolate, holds immense potential for accessible resources, including water, ice, and valuable minerals, which could fuel future space industries and alleviate terrestrial pressures. The prospect of life beyond Earth is a driving force behind Martian exploration. Even if microbial, the discovery of past or present life on Mars would fundamentally alter our understanding of biology and the universe itself. Understanding how life could arise and survive in extreme environments informs astrobiology and the potential ubiquity of life throughout the cosmos. The challenges of reaching Mars are immense, requiring unprecedented technological prowess. The journey itself exposes astronauts to prolonged radiation, microgravity, and isolation. Developing solutions demands innovative propulsion systems, robust radiation shielding, and advanced life support systems. each a monumental engineering feat, pushing the boundaries of human capability. Future Mars missions plan to leverage powerful new propulsion technologies, moving beyond traditional chemical rockets. Concepts like nuclear thermal propulsion, solar electric propulsion, and even more speculative ideas like fusion drives aim to drastically reduce transit times, minimizing crew exposure to radiation and making human missions more feasible and efficient. Radiation is a significant concern for human missions to Mars. Outside Earth's protective magnetosphere, astronauts are exposed to galactic cosmic rays and solar particle events, increasing cancer risks and other health issues. Developing effective shielding materials and understanding long-term biological effects are critical research areas, requiring cutting-edge materials science and medical innovation. Landing massive payloads and human crews on Mars presents another formidable hurdle. The thin Martian atmosphere is too dense for direct space-style entry, but too thin for effective aerodynamic braking, creating a terrible 7 minutes of terror during descent. Precision landing systems, parachutes, retro-rockets, and possibly advanced inflatable decelerators are all vital for safe touchdown. Once on the surface, establishing sustainable habitats is paramount. Future Martian settlers will need durable, radiation-shielded structures built either from Earth-launched materials or, more sustainably, using in-situ resource utilization (ISRU). Concepts range from inflatable modules to structures 3D printed from Martian regolith, adapting to the harsh conditions for long-term survival. Water is the holy grail for Martian colonization. Though the surface is arid, vast reserves of water ice are known to exist beneath the poles and mid-latitudes. Extracting and purifying this ice would provide essential drinking water, enable oxygen production through electrolysis, and serve as propellant for return journeys or further exploration, making ISRU capabilities fundamental. Generating sustainable power on Mars is critical. Solar panels are a viable option, though limited by dust storms and distance from the sun. Radioisotope thermoelectric generators, or RTGs, offer consistent power but use scarce plutonium. Future settlements may deploy advanced small modular nuclear reactors, providing reliable, high-density energy for long-term operations and growth. Producing breathable air and growing food locally are essential steps towards self-sufficiency. Closed-loop life support systems, recycling waste and water will be vital. Hydroponics, aeroponics, and advanced greenhouses, possibly utilizing Martian regolith as a growing medium after treatment, will provide nutrition, reducing reliance on costly Earth resupply missions and fostering self-reliance. Communication with Earth presents a time delay of 3 to 22 minutes one-way, depending on planetary alignment. This makes real-time conversation impossible, demanding significant autonomy for Martian crews. Developing robust communication networks, including satellites orbiting Mars and a dedicated deep space network, is vital for mission success and the mental well-being of colonists. The psychological impact of long-duration space travel and isolation on Mars cannot be overstated. Crews will face extreme confinement, risk, and separation from loved ones, requiring rigorous screening, extensive training, and robust support systems. Maintaining mental resilience, team cohesion, and a sense of purpose will be as crucial as any technological solution for their well-being. While terraforming Mars to become Earth-like is a distant, highly speculative, and ethically complex vision, it represents an ultimate long-term goal for some proponents of Martian settlement. Modifying Mars' atmosphere and environment over centuries, perhaps millennia, if even possible, would transform it into a truly habitable world for future generations, a monumental feat beyond current imagination. Returning humans from Mars is as complex as getting them there. The ascent from Mars requires powerful rockets, fueled potentially by propellants produced on the planet itself using ISRU, like methane and oxygen derived from atmospheric carbon dioxide and subsurface water ice. This capability significantly reduces the mass that must be launched from Earth, making round trips feasible. Mars is not a blank slate, devoid of history or potential life. The ongoing debate about planetary protection, preventing Earth microbes from contaminating Mars and vice versa, highlights critical ethical considerations. Preserving any indigenous Martian biology, if it exists, is paramount for scientific integrity, demanding strict sterilization protocols for all probes and human missions. The question of governance on Mars is already emerging. Who owns the resources? Who makes the laws? International treaties like the Outer Space Treaty provide a framework, but specific legal and ethical guidelines for off-world settlements, resource exploitation, and potential disputes will be essential, requiring unprecedented global cooperation and foresighted policymaking. The cost of reaching and settling Mars is astronomical, demanding significant public and private investment. This high barrier necessitates diverse funding models, international partnerships, and the innovative approach of private companies like SpaceX, which are driving down launch costs and developing reusable rocket technology, accelerating the timeline for human missions. NASA, the European Space Agency, Roscosmos, and other national agencies lead the scientific exploration of Mars, laying the groundwork for human missions. Their robotic rovers and orbiters meticulously map the planet, analyze its geology, search for water, and study its thin atmosphere, gathering vital data indispensable for future human pioneers. Rovers like Curiosity and Perseverance have revolutionized our understanding of Mars. Curiosity, landing in 2012, confirmed Mars once had conditions suitable for microbial life. Perseverance, landing in 2021, is actively collecting rock and regolith samples for eventual return to Earth, a crucial step in the Mars Sample Return campaign, paving the way for profound scientific breakthroughs. The scientific data from Mars orbiters is equally vital. Missions like the Mars Reconnaissance Orbiter and MAVEN map water ice deposits, analyze atmospheric escape, and monitor global weather patterns. This comprehensive data informs landing site selection, identifies potential resources, and helps mitigate environmental risks for future human explorers. The Mars Sample Return mission is a complex, multi-agency endeavor aiming to bring Martian rock and soil samples to Earth for in-depth laboratory analysis. These samples could decisively answer questions about Martian geology, past habitability, and evidence of ancient life, providing unprecedented scientific revelations invaluable for human exploration efforts. Private companies, particularly SpaceX with its Starship program, are spearheading the development of fully reusable, super heavy-lift rockets designed to transport hundreds of tons of cargo and eventually hundreds of people to Mars. This audacious vision aims to reduce the cost per launch exponentially, making larger-scale colonization economically viable for the first time. Blue Origin, Boeing, Lockheed Martin, and others are also contributing significantly to the Mars endeavor, developing landers, habitats, and launch systems. This collaborative ecosystem of public and private entities fosters competition and innovation, accelerating the pace of technological development and bringing the dream of Mars closer to reality. International collaboration is pivotal throughout this grand undertaking. Sharing resources, intelligence, and expertise mitigates risk, accelerates progress, and strengthens the ethical framework for humanity's expansion into the cosmos. Projects like the International Space Station demonstrate the power of nations working together for a common, ambitious cause. The first human missions to Mars will likely involve small crews, perhaps 4 to 6 astronauts, for relatively short stays, less than a month on the surface. These initial missions will focus on site reconnaissance, validating technologies, and establishing rudimentary infrastructure, paving the way for longer, more complex expeditions and eventual settlement. Subsequent missions will focus on building more permanent habitats, expanding power generation, and developing independent resource utilization capabilities. This phased approach allows for incremental learning, adaptation, and the gradual establishment of a self-sustaining outpost, step by careful step, transforming a desolate planet into a home. Beyond the initial settlement, the vision for Mars extends to terraforming. This hypothetical process involves thickening the Martian atmosphere, warming the planet, and potentially introducing liquid water and plant life over many centuries. While scientifically challenging and ethically debated, it signifies humanity's ultimate ambition to transform hostile environments into habitable worlds. The concept of a multiplanetary species ensures planetary protection not just from external threats, but from internal ones too. Should humanity ever face self-inflicted catastrophe on Earth, a robust Martian colony offers a sanctuary, preserving our knowledge, culture, and genetic lineage, guaranteeing the long-term survival of civilization. Building a civilization on Mars offers unparalleled opportunities for societal reimagination. It allows for the creation of new governance structures, economic systems, and social norms, unburdened by Earth's historical baggage. Mars could become a crucible for new ideas, a testing ground for a more sustainable and equitable human future. The economic implications of a Mars-based economy are immense. Beyond the initial investment, a self-sustaining Mars could develop its own industries, resource extraction, manufacturing utilizing Martian materials, space tourism, and even intellectual property born from unique Martian challenges. It could become a powerful new engine for human prosperity. The psychological fortitude required for individuals to commit to a multi-year, one-way or long-duration mission to Mars signifies a profound leap in human endeavor. These pioneers will become the new explorers, the true settlers of a new frontier, inspiring generations on Earth with their courage and unwavering commitment to humanity's future. Education and public engagement are vital components of the Mars endeavor. Inspiring the next generation of scientists, engineers, and explorers ensures a continuous pipeline of talent and support for this monumental undertaking. Popular culture, documentaries, and educational programs play a critical role in fostering this global interest, making Mars a shared dream. The sheer scale of the Mars endeavor dwarfs any previous human project. It requires long-term thinking, sustained political will, and a societal commitment spanning decades, even centuries. This generational investment underscores the profound belief that humanity's future lies beyond Earth, an enduring legacy for those who dare to dream of other worlds. The ethical guidelines concerning irreversible planetary modifications, like terraforming, remain a complex debate. Balancing humanity's drive for expansion with the responsibility to preserve potential indigenous life or unique geological features requires careful consideration, international dialogue, and a profound respect for alien environments. The scientific search for life on Mars extends beyond the surface. Subsurface environments, protected from harsh radiation and extreme temperatures, are prime candidates for hosting microbial life, past or present. Robots designed to drill deep into the Martian crust could unlock profound secrets about astrobiology and the potential for life elsewhere. The potential for a Martian brain drain, where highly skilled individuals leave Earth, is a concern. However, the innovation spurred by Mars missions often creates more opportunities on Earth than it removes, fostering new technologies, burgeoning industries, and a renewed sense of purpose that can rejuvenate terrestrial economies. Mars as a staging point. It's not just a destination, but potentially a crucial stepping stone for further human exploration into the solar system. Its resources, lower gravity, and comparative proximity could make it an ideal base for missions to the asteroid belt, Jupiter's moons, or even beyond, paving the way for interstellar travel. The health of future Martian colonists is paramount. Research on the effects of reduced gravity, isolation, and confined spaces simulates long-duration missions on Earth. Developing countermeasures for muscle atrophy, bone density loss, and psychological stress will be critical for maintaining astronaut well-being and productivity over years on Mars. Space debris is a growing concern in Earth orbit, and the same foresight must apply to Mars. Establishing clear guidelines for spacecraft disposal, responsible orbital management, and minimizing planetary contamination is crucial to preserve the Martian environment for future generations and scientific research, ensuring a sustainable presence. The philosophical shift from being a single-planet species to a multiplanetary one is immense. It expands humanity's horizons, challenges our terrestrial biases, and may even accelerate a more unified and collaborative global perspective as we face the common challenges of off-world expansion. Beyond the scientific and survival arguments, Mars exploration inspires. It captures the imagination, fuels childhood dreams of discovery, and fosters a sense of wonder and possibility that transcends daily life. This intangible benefit, the inspiration for future generations, is perhaps its most enduring legacy, driving societal improvement. The red planet's atmosphere, primarily carbon dioxide, poses challenges but also opportunities. This abundant gas could be used to produce oxygen for breathing and methane for rocket fuel through processes like the Sabatier reaction, making future missions significantly more self-sufficient and reducing the mass launched from Earth. Dust storms on Mars pose significant operational hazards. They can obscure solar panels, hinder visibility, and damage equipment. Designing robust, self-cleaning solar arrays and resilient robotics and integrating weather forecasting systems are crucial adaptations for long-term presence and ensuring continuous power and mobility. The question of Martian dirt, or regolith, presents both problems and solutions. While toxic with perchlorates, it also contains valuable minerals, water ice, and structural elements. Research is ongoing to ameliorate its toxicity for agriculture and utilize it as a building material for radiation-shielded habitats, turning a challenge into a resource. The concept of Mars time for colonists will present unique psychological and physiological challenges. A Martian day, or sol, is approximately 39 minutes longer than an Earth day, requiring constant adaptation to a slightly different sleep-wake cycle, further emphasizing the need for comprehensive psychological support. The search for subsurface caves or lava tubes on Mars is intensifying. These natural formations could provide ready-made, radiation-shielded habitats, offering protection from solar radiation, micrometeorites, and extreme temperature swings. Exploring these subterranean environments could drastically simplify initial habitat construction for settlers. Protecting astronauts beyond direct radiation shielding involves advanced medical treatments and genetic research. Developing pharmaceutical countermeasures, understanding individual genetic predispositions to radiation damage, and even exploring concepts like synthetic biology to enhance human resilience are frontier areas of biomedical research crucial for deep space travel. Food production on Mars will prioritize efficiency and nutrient density. Beyond traditional agriculture, culturing algae, fungi, and insect proteins could provide sustainable, high-yield food sources, minimizing water and energy consumption while maximizing nutritional output for a contained population, ensuring food security. The long-term vision of Martian self-sufficiency hinges on robust recycling systems. Every drop of water, every atom of waste needs to be reclaimed and reused. Mimicking Earth's natural ecological cycles within a technological framework is essential for closing the loop and preventing resource depletion for generations of colonists. The exploration of the Martian moons, Phobos and Deimos, runs parallel to the planet's colonization. These small, irregularly shaped bodies could serve as invaluable mining outposts for volatiles like water ice, or as strategic communication relays and waypoints for orbital missions, further expanding humanity's interplanetary footprint. The development of advanced robotics and artificial intelligence will be critical partners in Mars colonization. Robots can perform dangerous construction tasks, mine resources, and conduct maintenance in harsh environments, reducing human exposure to risk and enabling faster infrastructure development before and during human habitation. The legal framework for space resource utilization is still being defined. International cooperation is required to establish equitable and sustainable rules for extracting and utilizing resources on Mars and beyond, preventing potential conflicts and ensuring that the benefits of space exploration are shared by all of humanity. The race to Mars is not solely a competitive endeavor, but a collaborative relay. While private entities may compete on specific technologies or timelines, the ultimate goal of establishing a permanent human presence on Mars requires shared knowledge, coordinated efforts, and mutually beneficial partnerships across nations and industries. The cost-benefit analysis of Mars colonization extends beyond finances. The immeasurable value of scientific breakthroughs, technological spin-offs, planetary protection, and the inspiration of a multiplanetary future far outweighs the initial investment, offering a return on imagination that transcends monetary value. The discovery of evidence of ancient liquid water on Mars, proven by multiple missions, fueled the prospect of life. The presence of hydrated minerals, riverbeds, and subsurface ice suggests a past where Mars was warmer and wetter, raising tantalizing questions about its potential for habitability. Beyond water, the availability of other natural elements on Mars is crucial. Iron, silicon, aluminum, and titanium are abundant in Martian regolith, enabling localized manufacturing of tools, structures, and even advanced electronics. This shift from bringing everything to making everything on Mars is key to self-sufficiency. The engineering challenges are pushing the limits of materials science. Developing robust materials capable of withstanding extreme temperature swings, radiation, and corrosive regolith is critical for habitats, rovers, and life support systems, requiring innovative composites, alloys, and smart materials for resilience. The establishment of a permanent human presence on Mars requires the ability to produce rocket propellant on-site. The MOXIE instrument on Perseverance successfully demonstrated oxygen production from the Martian atmosphere, proving the feasibility of leveraging local resources for return journeys or future launches, a game-changer for interplanetary travel. Astronaut selection and training for Mars missions are incredibly rigorous. Candidates undergo extensive physical and psychological evaluations, mastering a vast array of skills from geology and engineering to emergency medical care and psychological coping mechanisms. They are truly the elite trailblazers of human endeavor. The medical challenges include managing long-term health issues in an isolated, remote setting with limited resources. Telemedicine, advanced diagnostics, and autonomous medical units capable of performing complex procedures will be essential, transforming space medicine into a highly specialized and self-reliant field. The role of artificial intelligence extends to daily operations and emergency response. AI systems can monitor life support, diagnose equipment failures, optimize resource consumption, and even assist with scientific analysis, providing vital support to human crews operating in challenging environments. Humanity's expansion to Mars will reshape our cultural narratives. New stories, myths, art, and music will emerge from the unique experience of living on another planet, defining a Martian culture that enriches and diversifies the broader human experience, adding new chapters to our shared history. Maintaining Earth-Mars supply lines, even with significant in-situ resource utilization, will remain a critical logistic challenge. Efficient freighter spacecraft, standardized cargo containers, and optimized trajectory calculations will be necessary to ensure a continuous flow of essential goods and new technologies to the Martian colony. The eventual development of an elevator to orbit or high-altitude platforms above Mars could revolutionize surface-at-orbit transportation, making access to and from the planet significantly more efficient and economical for both cargo and personnel, laying the groundwork for widespread colonization. The long-term effects of reduced Martian gravity on human physiology are still largely unknown. While 38% of Earth's gravity is significant, it's uncertain how it will impact bone density, muscle mass, and even embryonic development over generations. This makes Mars a living laboratory for human adaptation. Planetary defense, protecting Earth from asteroid impacts, can also benefit from Mars colonization. Establishing a human presence or robotic outposts further into the solar system allows for earlier detection and potential mitigation of such threats, turning Mars into a forward operating base for galactic security. The potential for a Martian nation to emerge, separate from Earthbound governance, is a fascinating future scenario. As populations grow and self-sufficiency increases, new political entities with unique identities and legal systems might arise, challenging conventional notions of sovereignty. The investment in Mars exploration fosters a grand challenge mindset globally, tackling problems on a planetary scale, from sustainable habitation to terraforming, generates innovative problem-solving approaches that can be applied to complex issues back on Earth, acting as a catalyst for terrestrial sustainability. The debate around artificial intelligence and its role in human expansion continues. While AI offers immense benefits in autonomy and problem-solving, ethical considerations regarding AI's decision-making in critical scenarios, especially those involving human lives on Mars, are paramount. The role of citizen science and public participation in Mars exploration is growing. Enthusiasts contribute to mapping projects, analyze drone imagery, and even help identify potential research sites. This broad engagement fosters a sense of ownership and collective participation in the Martian dream. The long journey to Mars will require advanced closed-loop hydroponic systems for fresh food. These systems can grow nutrient-rich produce using minimal water and space, recycling waste products back into nutrients, providing psychological comfort and dietary diversity for astronauts during transit and on the surface. Understanding Martian geology is critical for resource identification and hazard avoidance. Studying its volcanic history, impact craters, and tectonic activity informs decisions about where to build habitats, where to find water, and how to mitigate seismic risks for future settlements. The future of transportation on Mars will involve specialized rovers, pressurized vehicles for longer surface expeditions, and potentially even aircraft unique to the thin Martian atmosphere. Developing these diverse mobility options is crucial for extensive exploration and establishing new outposts. The challenge of dust management on Mars impacts every aspect of operations. Fine, abrasive Martian dust can clog mechanisms, degrade equipment, and pose a health risk. Developing advanced seals, coatings, and filtration systems is an ongoing priority for material scientists. The psychological effects of living in extreme isolation and confinement for years or even lifetimes must be carefully managed. Designing habitats with ample private space, incorporating virtual reality for connection to Earth, and facilitating meaningful social interaction are vital for mental well-being. Mars could serve as a valuable platform for astronomical observation. Its thin atmosphere and distance from Earth's light pollution provide unparalleled clarity for telescopes, potentially revolutionizing our understanding of distant galaxies, exoplanets, and the universe's origins. The ethical question of who gets to go to Mars is unavoidable. Initial missions will draw from highly skilled and trained professionals. As colonization expands, fair and equitable processes for selection, opportunity, and resource allocation will be necessary to ensure an inclusive multiplanetary future. Investment in space exploration, even during economic downturns, can act as a countercyclical force, stimulating economies through job creation in high-tech sectors, driving research and development, and fostering innovation, effectively becoming a societal engine for growth. The search for extremophiles on Earth informs the search for life on Mars. Studying organisms that thrive in harsh conditions, like intense heat, cold, or radiation, provides models for what kind of life might exist on Mars and where to look for it, informing astrobiological strategies. Understanding seismic activity on Mars, or Marsquaks, is important for habitat design and resource exploration. Missions like InSight provided crucial data on the planet's interior structure and ongoing geological processes, vital for ensuring the safety and stability of future settlements. The history of exploration teaches us that humans adapt and thrive in new environments. Just as pioneers settled across continents, future Martians will develop unique tools, customs, and survival strategies, forging a self-reliant society shaped by their new planetary home. The concept of off-world insurance for humanity means preserving not just our physical existence, but our cultural heritage. Digital archives, seed banks, and historical records could be stored on Mars, safeguarding our collective knowledge against any terrestrial calamity. The ethical responsibilities of being caretakers of another planet's ecosystem, even if it's currently barren, are profound. Avoiding irreversible contamination and committing to long-term environmental stewardship will be critical for any human presence, marking a new era of cosmic responsibility. The challenge of waste management on Mars is significant. Every piece of equipment, every package, every human byproduct must be either recycled, repurposed, or safely stored. Developing advanced waste-to-source technologies is crucial for long-term sustainability and preventing pollution of the new world. Space tourism to Mars, while far off for commercial ventures, is an intriguing future possibility. It could popularize space travel, generate revenue for infrastructure development, and offer a transformative experience, shaping a new market for adventure and exploration. The sheer scale of rock and regolith needed for construction on Mars makes ISRU paramount. Robots extracting and processing these local materials into bricks, concrete, or protective radiation shielding dramatically reduces the logistical burden from Earth, enabling truly self-sustaining settlements. The development of advanced robotics for extreme environments on Mars also benefits Earth. Innovations in autonomous systems, remote sensing, and resilient materials can be applied to hazardous terrestrial tasks like disaster response, deep-sea exploration, or industrial automation. The search for perchlorate-tolerant crops or methods to neutralize perchlorates in Martian soil is central to future agriculture. If Martian regolith can be safely and effectively used as a growing medium, it vastly expands the potential for food production on the planet. The concept of synthetic biology could play a transformative role on Mars. Designing microorganisms to produce specific compounds, break down toxins, or even assist in terraforming processes could accelerate the habitability and resource generation on the planet. Mars can be a laboratory for understanding life's boundaries. Studying how Earth microbes might survive or adapt to Mars conditions, or conversely, how potential Martian life forms might exist, offers profound insights into astrobiology and the resilience of biological systems. The evolution of human language, culture, and even physiology might occur over millennia on Mars. Generations adapting to different gravity, environment, and social structures could lead to a distinct Martian humanity, a fascinating prospect for future anthropology. The transition to a multiplanetary species emphasizes a greater understanding and appreciation for Earth. Seeing our home from the cosmic perspective highlights its fragility and uniqueness, fostering a renewed commitment to its preservation and sustainable living practices. The race to Mars is more than a competition among nations or corporations. It is a collective human endeavor. The challenges are so immense that they necessitate collaboration, shared knowledge, and a unified vision, making it the ultimate test of our species' ability to work together. The psychological impact of seeing Earth as a distant star, a pale blue dot, changes one's perspective permanently. This cosmic awareness can foster universal empathy, transcending petty terrestrial conflicts and uniting humanity under the vastness of the universe. Building self-sufficient habitats demands closed-loop environmental control systems. These complex systems meticulously manage air purification, temperature regulation, humidity, and atmospheric pressure, creating a stable, Earth-like environment within the Martian harshness. The history of human exploration is one of gradual extension. From coastlines to continents, then to mountaintops and the poles, each step pushes our capabilities. Mars is simply the logical next step in this millennia-long journey of discovery and expansion. The long-term health of Martian settlers will be bolstered by advanced biometrics and real-time health monitoring. Wearable sensors, AI-driven diagnostics, and even remote surgical capabilities will ensure immediate and preemptive medical intervention in an environment with no immediate rescue. The concept of humanity itself will expand and evolve with Martian settlement. Will Martians be Earthlings, or a new branch, a Homo Martianus? This philosophical question deepens our understanding of identity, belonging, and the very definition of our species. The development of advanced robotics for exploration and construction on Mars requires significant breakthroughs in autonomous navigation, dexterous manipulation, and extreme environment endurance, propelling the entire field of robotics forward. Establishing a reliable communication network between Earth and Mars involves a constellation of dedicated relay satellites and deep space ground stations, ensuring continuous data transfer and vital communication links for human missions and future colonies. The financial self-sustainability of a Mars colony depends on developing viable internal economies and valuable exports. Beyond scientific data, unique Martian products, advanced technologies developed for the extreme environment, or even unique Martian artistic expressions could create a distinct economy. The long-term effects of cosmic radiation on electronics and materials require specific material science research. Developing radiation-hardened components and self-healing materials is critical for ensuring the longevity and reliability of infrastructure on Mars. Mars exploration drives international law and policy development in unprecedented ways. Issues ranging from resource ownership, environmental protection, planetary defense, and the rights of future Martian inhabitants necessitate new legal frameworks developed through global consensus. The prospect of developing a Martian ecosystem via terraforming, though centuries away, ignites profound scientific discussions. It forces us to understand complex planetary systems, the delicate balance of life, and the potential for humanity to become a constructive force in shaping new worlds. The exploration of Mars pushes the very definition of human endurance. Astronauts will face profound challenges, but their resilience, determination, and ability to adapt will inspire an entirely new understanding of human physical and psychological limits, expanding what we believe is possible for our species. The quest for life on Mars extends to the possibility of biosignatures in the deep subsurface, beyond the reach of current rovers. Future missions might involve sophisticated drilling equipment capable of reaching depths where liquid water and dormant life could potentially hide from the harsh surface conditions. The engineering precision required for Martian missions is astounding. From navigating spacecraft across millions of miles to deploying complex instruments on a remote planet, every calculation and every component must be meticulously designed and tested, leaving no room for error. The long-term viability of Mars colonies depends on developing capabilities for complex manufacturing and repair on-site. This includes 3D printing of spare parts, advanced robotics for intricate repairs, and even localized fabrication of new, custom components. The potential for scientific breakthroughs from Mars is boundless. Discoveries about planetary formation, the ingredients for life in the universe, or even entirely new forms of geology could revolutionize our understanding of science, pushing the frontiers of knowledge in countless fields. The role of international space law, specifically the Outer Space Treaty, will be tested by the reality of Mars colonization. Debates around property rights, resource exploitation, and potential sovereignty claims will require continuous negotiation and adaptation to ensure peaceful and equitable settlement. The development of habitats for Mars includes considerations for protection against micrometeorites. Designing multi-layered walls, incorporating sacrificial shielding, and potentially burrowing structures underground are strategies to safeguard human settlers from space debris. The shift towards reusable rocket technology, pioneered by companies like SpaceX, is fundamentally altering the economic landscape of space travel. By significantly reducing launch costs, reusability makes frequent, larger-scale missions to Mars and beyond financially viable, accelerating colonization efforts. The educational outreach inspired by Mars exploration can transform STEM education. Engaging children and students with real-world missions, challenges, and scientific discoveries makes learning tangible, exciting, and directly relevant to humanity's future in space. The ethical considerations of creating an artificial ecosystem on Mars, or terraforming, are profound. Balancing the desire to make Mars habitable with the unknown potential for existing life, or the implications of fundamentally altering a planetary body, requires deep philosophical and scientific debate. The long-term success of a Martian colony hinges on its ability to attract and retain a diverse population. Beyond engineers and scientists, future Mars will need artists, teachers, doctors, farmers, and entrepreneurs, building a vibrant, self-sustaining society. The psychological impact of the overview effect, seeing Earth as a fragile single entity from space, may uniquely shape Martian identity. Distance could foster a new sense of unity, a shared responsibility, and a deep appreciation for the cosmic context of human existence. The development of closed-loop water recycling systems is paramount. Every drop of water on Mars, whether brought from Earth or extracted from ice, must be meticulously purified and reused for drinking, hygiene, and plant growth, minimizing loss and maximizing resource efficiency. The ongoing search for biomarkers on Mars, specific indicators of past or present life, remains a top scientific priority. Instruments on rovers and orbiters search for organic molecules, methane plumes, or unique mineral formations that could point to the existence of Martian biology. Establishing communication protocols that account for the significant time delay between Earth and Mars is critical. Astronauts will require high levels of autonomy, robust procedures for decision-making, and communication strategies that minimize frustration and optimize information exchange. The economic benefits of Mars exploration extend to Earth in unexpected ways. Innovations in water purification, sustainable energy, advanced robotics, and life support systems, all designed for Mars, can dramatically improve quality of life and resource efficiency here on Earth. The race to conquer Mars is a testament to humanity's enduring spirit of adventure and ingenuity. It represents our collective aspiration to push beyond current boundaries, to seek knowledge, and to ensure a vibrant future for subsequent generations, forging a new destiny among the stars. As we look towards the red planet, we recognize that the future of humanity isn't confined to a single world. It spans the cosmos, driven by our insatiable curiosity and the profound understanding that to survive and thrive, we must become a multiplanetary species, securing our place in the universe.